Hey, so thanks everyone for coming to attend this session. I'm Sunil Patil and I'm here with Sridhar Reddy. We work for MapR. And today I'm going to talk about designing and implementing IoT solution using open source technology. So basically, for that what we thought is instead of talking about IoT in abstract terms, let's take a use case. Let's imagine that we are working for a big retail company, maybe say Walmart or Costco or something big, and we got into project of building temperature monitoring for them. So for example, what we are tasked with is we have to put these temperature monitors in each of the stores, in each of their aisles at certain distance, and then we want a central dashboard where I can go and see that, hey, what is the temperature in, let's say, San Jose store in particular aisle. You might want to do that for multiple reasons. You might want to do that just to make sure that your ACs are working as expected. Once you have that working, you might want to tune you might want to tune your AC temperature from central location. Or you might be creative. You might want to say that, hey, I have a store in San Jose and one store in Fremont. Let me see if I change or if I set temperature of my San Jose store, let's say few degrees centigrade below the normal, does that prompt people to buy maybe more sweaters or more jackets? So there could be multiple things you might want to try. Now, basically we want to build a temperature monitoring application. For that we would need a temperature sensor. So let's imagine we have a temperature sensor which reads temperature once every second and sends it to some kind of central location. So for something like that, if we just do some rough calculation, so let's say a sensor reading one record every second means 3,600 records in 1 hour, 24 hours in a day, 365 days. That means you are looking at about every sensor reading about 31 million times in 1 year. Now let's imagine that every time our sensor reads data, it generates about 100 bytes of data and it is sending it to a central location. So we multiply 31 million by 100 bytes. So each of your sensor is going to generate about 3.1 gigabytes of data per year. So I'm talking about single sensor. But if you do a quick Google search on some of these big stores, so for example, Walmart has 6,500 stores in US. Let's imagine the store that we are working for has, say, 6,000 stores in US. And you might have seen these stores. They are like gigantic. So imagine each of these store has 50 aisles. And we decide that in each aisle, I'm going to put 4 sensors. So 50 aisles multiplied by 4 sensors in each aisle is 200. Multiply by 6,000 stores. So you are looking at 1.2 million sensors. And if you multiply 1.2 million sensors generating 3.1 gigabyte data per sensor each year, you are looking at about 3.6 petabyte of data in a year. So to solve this kind of problem, you need architecture which can scale horizontally, or which can scale linearly, and you definitely need big data for something like this. Now, let me show you a demo of this. One issue is we ran, so for that, I have this device. I don't know how many of you have used Arduino in the past, but this is an Arduino device. We ran into problem that, so which one? You want to take this? So what we'll do is, I have this Arduino and I have a temperature sensor attached to it. Right now, it is reading the room temperature, okay? So basically, yeah. So right now, this sensor is reading a room temperature. And on this device, I have 2 things. I have this red thing, which is a teeny tiny thing, LED, and I have a sensor. So right now, the temperature that, I'll show you the dashboard. So the temperature is about, let me see. So the temperature, the current room temperature is about 2187, something like that. Now I have some ice in this flask. So what I'll do is, I'll put,
what happened?
it's not displaying?
Okay.
Or maybe I'll just put in here. should we switch back the UI? So basically what I'm showing is if the yeah, so I put the sensor in ice, and what should happen is in about 1 minute or so this LED should light up, and I'll show you the UI for that as well. So basically imagine you have these sensors installed everywhere, and your use case is you want to see whenever temperature either falls below 10 degrees centigrade or goes above 40 degrees centigrade, you want somebody to take a look at that. Like, you want, you might want to flash instead of LED a bigger light or something, so that a store employee knows that something is going wrong, and they should start taking a look at that sensor. 2.06. And one other thing with this sensor is, like, when you put it in ice, the temperature doesn't drop right away. Instead, it takes few seconds before it drops. So let me do this. Now you can see the LED lit up. So it takes few seconds because this sensor, it doesn't just drop from 20 to 0 as soon as you put it in ice. It takes few seconds. Let me switch back the UI. Okay. Just to make sure that I'm not showing the already cooked up data, let me show you few things here. So when you have Arduino, right? Okay. When you are using Arduino, they basically don't have a log file or something. Instead, the way you see what your Arduino is doing is by connecting this kind of serial monitor to it, and from your program, you write some messages that you can monitor from your machine. So, and right now I have, like, this type of data flow here. So you can see I have I have a sensor on the left hand side, and I have this dashboard, I have a Grafana dashboard. So you see initially the orange line that you see, it is the temperature line. And as an application, like initially I said that if temperature goes below 10, that means something bad. Same way, the red line that you see is 40 degrees centigrade. If I were to put this in like really hot liquid, it would go that way. You saw like before, like till about 4:15, the temperature was about 44, and at 16:16, when I put the sensor in liquid or in ice, the temperature dropped and it went down to about 0.62 degrees centigrade. So that's a yeah, and now maybe you might want to hold, so if you want to hold on to it. So what is happening is, now if you see, I am showing you about 3 windows. So the first window is a Mosquito server where the messages are coming in, and don't worry, I'll go through details of each of this. Then you see this window where you can actually see the temperature. I'm holding on to it, so the temperature is going up slowly and slowly. Like see, now it went up to 20.19, 20.50, it is going up. And I have a Spark job, which is actually reading messages, processing, and putting them in Flux DB, and that's the chart we are looking at. And this is another broker. So let me come back to this demo. So basically what we are doing is, I showed you the sensor on the left hand side and the LED, both of them on Arduino, and Grafana on the right hand side. Now, this one, you might say that, hey, you have a single sensor, why do you even need anything related to big data? But as we talked about, when you actually deploy this in real world, you would have millions of sensors. And when you are building an IoT application, you might want to think about it in terms of layers. So basically, what I mean by that is, right now while building this demo, I made certain choices, like, I wanted to use Grafana for showing visualization, or I wanted to use Spark for computation. But you might be comfortable with some other tools. But if you think about your application in terms of layers, for example, like, I have these 7 layers. So for one common example is, some people like Spark, some people like, something like Storm and things. So when you think about your architecture in terms of layers, one advantage it will give you is, If you look at the compute layer, right now I'm saying that it is responsible for reading from Kafka and writing it into Flux DB. So either you could do it with Spark or you could do it with Flux DB. So there are different choices, but basically what I'll come back to is when you are building IoT application with big data, you might want to think about it in terms of layers, and then you can go about evaluating different options that you have for each of the layers. And now we'll start digging deeper into each of the layers. And one thing is, I know I have like little bit more content than what I can fit in 40 minutes. So what I'm doing is I'll start with the sensor layer, and I'm assuming like most of the people here are like comfortable with big data, so I'll spend more time on this. But and I might, if I don't get much time, I'll run through Spark instead of spending more time. Same way, if you are not able to see this demo up close, you might want to stop by at the MapR booth. There you can put the sensor in ice and you can see everything. So please visit MapR booth if you want to play with this demo. So coming back to the sensor layer. So the first thing that you need for IoT application is your sensor layer, which is the leftmost side. So basic thing with IoT applications is you need components which can interact with the physical world, and those components are divided into two basic categories. First is sensor. So sensor means anything which can either detect or measure particular physical property. For example, in this demo, we wanted to show, we want to read temperature. So for that, we are using temperature sensor. Same way, you might need other type of components. So basically you might want to say that, hey, I am doing some calculation. Based on that, I want to control something. So for example, in my demo, like when the Spark figures out that your temperature is beyond certain limit, it wants to send a signal back to my IoT device so that LED can light up. So that kind of processing, the other way around flow is called actuator. And I'm using LED as an actuator, but you can, if you are building, let's say this temperature monitoring application, you could very well use a servo motor, and you can say that, hey, if temperature goes below 10 degrees centigrade, maybe start closing your AC valve so that you are pushing in less colder air. But if temperature goes above a certain degree centigrade, you might want to open the AC valve a little bit more. So same way, you have other options for both sensors and actuator. Now when it came to choosing, so the first choice I had to make for this demo was, hey, what sensor I want to use. So I looked at two different options. One is this waterproof temperature sensor called DSB1820. DSB18B20, or other is this small sensor called DST22. For my particular demo, I use DS18B20 because I can push it in, I can put it in hot or cold water and the liquid or the temperature goes up suddenly. But if you are using this for your home automation, I would suggest use DST22 because you see it is much smaller. It is easier for you to put it in window or something like that. Once you use the sensor, once you picked up your sensor, whatever is your use case, once you picked up the sensor, the first thing you would have to do is you'll have to figure out how do you connect it to some kind of center, something which has some amount of computing power. So I'm going to talk more about Arduino in the next section. But once you choose the sensor, the first thing you need to figure out is how do you connect it to your controller. And one thing is, like most of the sensors, they have about 3 wires. One is for voltage, another for ground, and third one for data. And whenever you buy a sensor, you will see a technical spec for that sensor. Or easier way of doing it is, you just search in Google about DST22 Arduino pin layout, and you will find something like this. So basically, what it will show you is how do you connect the sensor to Arduino. Right now, the black strips that you see on both sides, they are called general GPIO, that is general purpose input and output. So basically, the sensor documentation will tell you that push this pin or connect this pin to let's say VCC or whatever. Like you can look at the pin layout and you would be able to figure out how to connect between them, and you would also see what kind of registers you need. Same thing you need to do for actuators as well. Now in my case, I had a simple LED which only needs voltage and ground and kind of LED in between. So you could also find a sample of how do you connect LED to Arduino. Only thing you need to remember in this case is you see the one pin of my LED is connected to pin 8. That means based on my digital signal, it will turn on or off. If you want that LED to be always on, you might want to push it in the VCC. Now, like, other thing is, I don't know, like maybe you might have felt that, temperature monitoring is not the best possible use case. You might have something else in your mind. Or you might say that, hey, I don't work for Walmart. How does this apply to me? In that case, what I'll say is, you could use a lot of this for your own learning. For example, the demo that I am showing, this Arduino plus sensor, you can get all those components for less than $20. So if you want to say that, hey, I want to learn about big data, so let me get, let's say, 5 of these. I'll put each of that in each of my room, and I can collect about 20 GB of my own data every year. Or you might have some other use case in your mind. So for example, Walmart might say that, hey, it's 1.2 million sensors. We are not necessarily interested in temperature. But instead of that, let me put a kind of distance sensor or proximity sensor so that I can see how many people are entering in each of my aisles. So that I can figure out if I am putting, say, cereal A in my first aisle, is it getting enough traffic for me to justify that? So basic idea here is you decide what your use case is, you figure out what sensor you want to use, and just do a Google search for whatever you are interested in. You would find a sensor, you start from there, but rest of the stack remains same. The next thing you need for this is you need a controller. So, and the reason for that is these sensors, they are not smart enough, or they don't have processing power to do any kind of computation. So you need a device, you need something which will connect to sensor, read the temperature or whatever physical property you are reading, convert it into message, and send those messages to your, say, IT infrastructure. Other way also, whenever your IT infrastructure wants to say that turn this fan on or that light off, it will send some message back, and based on that, you would want to control that actuator. So you need basically a computing layer which can read from sensor, same way control your actuator. For that, the choice that I made is I am using Arduino. So Arduino is basically open source platform for building electronic projects. So what it has is, it has a specification. So that means there are multiple types of Arduino boards. I'm just showing you 2, but there are, I guess, more than 10 types of different Arduino boards. As long as they meet the hardware criteria, you can call it Arduino. And in addition to the hardware specification, there is also a IDE. So there is a Arduino IDE that you could use for programming, and that IDE looks something like this. So basically, for programming Arduino, you use a simplified version of C. This is how the IDE looks like, and basically in Arduino, you get 2 simple methods. One is setup and another is loop. So whenever you power your device, what it will do is it will execute your setup. After that, it will keep executing your loop method. So based on your logic, you would write something in setup, something in loop, then you start from there. Now in my use case, what I wanted to do was, I wanted to read temperature using DSB 1820. So for that, the first thing I need is the driver for that sensor. So in Arduino, you could, they have something called manage libraries. You open that UI, you search for the driver for it. For example, the DHT sensor that I talked about, it's the second from bottom. That's their driver library. Or if the demo that I am using uses the last temperature, which is in the middle. So the next thing you do is you download the library. Once the library is downloaded, you start writing your code in kind of C. Here you see the first statement, like first few lines that I have, they include the necessary libraries in my project. So one wire and the last temperature, that's the driver code. Next, This is how you would write the setup. So what I'm doing here is I'm saying that my temperature sensor is connected on pin number 2. That's the first line. And then I'm passing it to, I'm creating object of the last temperature, and I say sensor begin. So it starts interacting with the sensor. After that, you write a loop method. So basically, loop method is something that will just keep executing and again. So first thing I'm saying is, hey, I don't want to just keep hammering my sensor. Instead, what I want to do is, I want to read a temperature, go back to, and then wait for 1 second before reading it again. So in my loop, first statement I have is delay. After that, I can say sensor.request temperature, so that the sensor's temperature is ready. And then you see the last line, sensor.get temp C by index. That's how you are able to get the temperature. Once your code is ready, what you do is Arduino ID would have a button called compile or upload. You click on it. Arduino would take that code, compile it into binary format, and then I don't know if you are able to see it, but I have a micro USB cable connected to this thing, which is another end of it is in my computer. So what I do is I say upload, and I upload my code onto Arduino, and then it starts running it from there. But once your development is done, I can take it out and I can connect it to, right now, see, this is a normal mobile charger. I can connect it to, I can use that to power it. Once your code is uploaded on Arduino, you are all good to go. Like whenever it starts, once it gets power, it will start executing it. The other type of device that you might have heard more about is Raspberry. So Raspberry, for all practical purposes, is a mini computer with a difference that it has the GPIO pins. The strip you see on the top right side, like few pins, so that's the GPIO. So Raspberry, it's basically a computer where you get HDMI pin, so you can attach it to your monitor, you can attach a keyboard and mouse to it. But additional thing is, using those 32 pins that you see on the top, you can connect it to a breadboard like this, and you can start connecting your sensor and actuators to that. And I would recommend start with Raspberry because I guess most of us are more familiar with programming languages like Python and Java. So Raspberry, you can connect it to monitor. It also has a Python IDE. You can start building your code there just so that you get feeling of sensors. And this is how I wrote the same code using Raspberry. So basically, this is a Python program. At the top, you see I have the Python modules, which are the sensor drivers. That's for Adafruit DST, which is this one. Then it's not like a normal program like you see besides that green block, rest of the code is just to read the different configuration parameter from system out. But the last block you see, that's where I am calling adafruit.readretry, and I'm telling it I have a sensor attached on say particular pin. I want to read the temperature. And once this kind of Py code is ready, you could either write it inside the Raspberry or you write it on your Mac, you SSH into it, and then you start executing it. So basically, Raspberry has a Linux operating system on top of it. So you could use it as your normal computer. And you don't need to convert into binary. And one other good part with Raspberry is it has about 1 GB of memory. So you could run your Java code, you could install Java on that, you could do you could use it as a normal computer. These are just some differences, like Raspberry is called a microprocessor, whereas Arduino is a microcontroller because Raspberry has a OS. Arduino doesn't have anything. It doesn't have a OS. You compile your code, give it to Arduino, and it keeps executing it again and again. The next thing, and which is maybe more relevant in terms of big data, is protocol layer. So protocol layer is the one who is responsible for communicating between IoT device and your IT infrastructure. So what I mean by that is, now let's say you have this Arduinos or your IoT devices running, they want to send some data to your IT infrastructure. You need somebody who can receive those messages and then start the processing. So for that, you need a protocol, like it is a protocol that is used between your IoT device and your IT infrastructure. And so the first question that you would have is, hey, why do I need a different protocol for IoT devices? What is so special? So these IoT devices, they are really constrained. For example, like it is very common for a IoT device to have 8-bit or 16-bit processor. For this demo, the ESP8266 that I am showing you, it is a 32-bit processor, but it has only 1 megabyte of RAM. And if you ever looked at Kafka client, the Kafka client jar alone is 4.5 or about 5 megabytes. So you cannot use Kafka on this. So basically, IoT devices don't have the sufficient processing power. They don't have enough memory to run something heavy like Kafka. Other thing is, you might have an IoT device running on a truck or maybe inside a BART or some kind of public transport system. So they might not get consistent network connection. They might be in and out of your network. So there are some additional requirements for that. Another thing is, these IoT devices can generate huge amount of data. So for example, the sizing we looked at, imagine you are getting like about 1.2 hits per second from 1.2 million devices. It's like huge amount of data. So you would want to make sure that your network communication is as efficient as possible so that your bandwidth usage remains low. And last thing is, these IoT devices, most of the time they would be powered by battery. And you would want to make sure that you use that battery as efficiently as possible. For example, you might have an IoT device installed on maybe Golden Gate, which is looking at what is the stress level at maybe say particular part of the bridge. And I wouldn't want to go on Golden Gate to replace battery for that device. So I would want to make sure that it lasts as long as possible. So for these kind of special requirements, you need, IoT industry has defined two protocols. One is MQTT and another is COAP. But before I move on, I'm just showing you the Arduino ID connected to my ESP8266. And you can see in the black section, the first line, it says, I have at the most 1 megabyte of memory. And out of that, my program is using about 32 kilobytes. Now, the first protocol that we'll look at is MQTT, which is Message Queue Telemetry Transport. So this is an open protocol, or this is a OASIS standard, which was defined by IBM, but they donated it to Eclipse PAHO. So it's an open standard. There are about maybe 40 different clients that you can use, which are MQTT compliant. Most of the big advantage with MQTT is you can find a client, MQTT client, which is less than 30 kilobytes in size. So the one I am using is about 20 kilobytes. And then the biggest thing it has is it uses, being a network protocol, what it does is it uses a very small packet size. So basically the header is about 2 bytes. Basically MQTT works on TCP, but MQTT SN, the new protocol that is coming up, which is, it is supposed to work on UDP, and basically UDP is more network efficient compared to TCP. Other thing is, the MQTT protocol is easy to parse. By that I mean it's a binary protocol. Like HTTP is a ASCII protocol, so it's easier for humans to read, but it's not easier for devices to read. MQTT is binary, so it's easier for devices to read it by doing byte manipulation. And other thing with MQTT is it has this concept of quality of service. So basically you can say that, hey, this is, my device is running on maybe a truck which is moving around, and I can say that I want every reading to be delivered at least, at the most once. So if I am out of network, it won't deliver the message and that will drop off. But you might say that I want to make sure that the message is delivered at least once. So it will hold on to that message, maybe by on disk, and once it gets into network, once it gets network connection back, it will try to send those messages. And third one is exactly once, that means publisher to subscriber, it will do it only once. Now, the battery part that I talked about, like this is some benchmark I found out on internet about comparing between MQTT and HTTP. So when Facebook was building a mobile application or the messaging application for mobile, they did a comparison between MQTT and HTTP. And I don't know if these stats came from Facebook, but basically right now they use MQTT for their messaging application. And it turns out that MQTT is much better at using battery. When you are using MQTT, basically it's like your normal JMS, like it is a request response system in which, like in this case, like you might have different sensors. So my sensor in Fremont Isle 1 might be pushing its temperature reading on store Fremont Isle topic. So yeah, other thing is the MQTT topic names are arranged in hierarchy. So I could have a topic name store Fremont Isle 1, store Fremont Isle 2, store San Jose Isle 1. And then like the sensors will keep pushing data on the topic that they have chose. And the subscriber can say that I am interested only in all the aisles in Fremont, or I could say that I am interested in all the stores. So subscriber can pick using the wildcard what all topics it is interested in. When you are dealing with MQTT, you need a server and a broker, so basically a client. So in this case, I am using Eclipse Mosquito as my MQTT server, and then I am using Eclipse PAHO library or PubSub client in this case, which is basically MQTT client. So you need somebody server as well as client, and you can get both of those from Eclipse. So once you have that ready, what you can do is you can write code something like this. Here, I am saying that, okay, how does my sensor connect to Wi-Fi? What are names of my top, sensor topic as well as actuator topic? Then in the setup, I have some code which says first establish Wi-Fi connection, then establish MQTT connection, and here this is the part where I am actually reading the temperature and sending it to MQTT. So you see the loop method, it reads a message or it reads temperature every single second in the send message method, and then it is publishing that in form of CSV. And the callback is when the actuator says that I need to turn the LED on, that's where the callback will get called. And you can see I am turning in the last 3 lines I am saying LED if the alert was set to 1, set alert LED to high or low. So that's how you can turn LED on and off. Other protocol is COAP, but I'll just skip those slides. But it's a very efficient protocol that is coming up. Now the next part is about the messaging layer. So you might say that, hey, if I have MQTT, why do I need additional messaging layer? And I'm saying that messaging layer would be responsible for taking messages that were sent to MQTT broker and giving it to your computation layer, which is Spark in this case. The reason you need a layer like Kafka in between is because Mosquito, like if you have, let's say, let's say you have million sensors, and for to handle that much of traffic, you need maybe about, say, 10 instances of Mosquito. Then you would have to install them on 10 machines, but they don't know how to talk to each other. Same way, when it comes to consuming messages, let's say you want to process all those messages using Spark, then Spark will have to figure out how to talk to all those 10 instances. You could very well put a IP sprayer or some kind of HA proxy in between on both sides, but like Spark can't do that. You would have to run 10 different applications talking to each of those. And other thing with this is you also need to remember that once you deploy your IoT devices, there is no downtime. Your sensors will keep sending data continuously. So if you want to update your computation code, you need a layer in between which will say that let the sensors keep sending me data, I will hold on to them, and once my Spark code is updated, it will start consuming the messages again. So if you use Kafka, so if you take out the load balancer and if you put Kafka in between, then what would happen is, your devices would still send data to a load balancer which will spray between your 10 or 20 MQTT servers, and every MQTT server, and you would have a component which would read from MQTT and write it to Kafka. And once data is in Kafka, you could use something like Spark for consuming those messages. And one thing is, basically, if you look at MQTT and Kafka, by default, they don't talk to each other. So in order to build this demo, I built like, two bridges. One bridge which can read from MQTT and write to Kafka. Same way, I have another bridge which can read from Kafka and write into MQTT. So you basically subscribe to a topic and just keep writing from here to there. Now the next layer we can talk about is the computation layer. So the computation, so the first question would be, do I really need something like Spark here, or should I just say that my MQTT starts writing on, let's say, local file, or it can start writing into, HBase or some kind of TSDB directly. My perspective is you would need computation layer because you might want to have some kind of intelligence in it. So for example, when your sensor data is coming in, you might want to say that for every sensor, I want to attach geolocation for that. So I know, if something is going wrong, I know exactly where that sensor is located. Or I might have a predictive model which will say that, let's say instead of a retail store, if we were working for oil and gas company, we could say that, when the data is coming in, I want to learn what happens in case of failure. So next time when my, say, one of my machine is going to fail, before that my predictive model can look at the data generated by machine and predict that this is going to fail in, say, next 15 minutes or 20 minutes. So if you have a compute layer in between, you would get ability to do your machine learning here. And you can give some intelligent feedbacks which goes something beyond saying, hey, if temperature is above 10 or below 10 or above 40, do something. Instead, you would want to give more intelligent feedback. This is the Spark streaming slide, so I will skip it. For this particular demo, what I did is I integrated Spark with rules. So I could write rules like this. So you can see the first rule says, if temperature goes below 10 degrees centigrade, send alert. But when it comes to high temperature, I can say that, hey, Arizona is a really hot state. So I can say that in case of Arizona, even if the temperature goes up to 60, I'm okay, don't send an alert. But for other states, I can say that, if temperature goes above 40, I want to send an alert back. So for those kind of things, if you have a rules engine integrated, like, all that business logic can stay out of your actual code and you can change it more dynamically. The next layer I'll talk about is the storage layer. So if you think about it, most of this sensor data is time series data. So basically what I mean by that is you would want to read temperature or whatever physical property you are reading in terms of time. You would want to say that I want to see what was the highest temperature on, say, last Wednesday, or what was the highest temperature in last quarter, or how many entries I received in last 3 months. So for storing that kind of data, you use time series databases. And these time series databases, they are specifically built for storing, storing time series data in efficient manner. They can even compress your data. And they can handle high amount of load. They can do some amount of aggregation like count or minimum and maximum. So I am using Flux DB, which is a time series database. And when it comes to time series database, there are kind of 3 important points. One is, in case of time series, you would have to first choose the data point. Basically, in our application, what we are saying is, I want to see how the temperature varies over a period of time. So my data point is time versus temperature, which is the orange line. The matrix is getting generated once every second. So sensor temperature is 1 second. And then right now I showed you with a single sensor. But if I had, say, 10 sensors, I could say that, I could attach tags to that data. I could say that for this particular record, sensor ID is 2, and location, if this was your home automation project, you could attach a location saying that sensor 1 is in my bedroom 1 or sensor 2 is in my bedroom 2. So you could add those additional location related tag. That way you have a way to slice and dice that data. Once you have matrix and tags put together, they are called time series. I'm using Flux DB, and this is how my data looks like. And basically Flux DB, what it does is it lets you do SQL queries on top of your data. So when I do select star from pump, you can see rows. You can see the first record says the time when I took the reading, the sensor ID, which was 1, and what was the current temperature. In this case, almost all the records have same temperature, but whatever variation, you could have seen it here. Now the last layer is the dashboard layer. If you are using a time series database, then there are a lot of visualization tools that you can use, which will provide you that out-of-box integration with the time series database. I decided to use Grafana in my case. If you have Grafana, you want to connect it with Influx DB, it's pretty easy. You just go and give it details about the URL field you see in the middle. That's where, since my Influx DB and Grafana are sitting on the same virtual sandbox, I'm saying that the URL for Influx DB is localhost 8086. I'm looking at database called MyDB and user ID password, that's towards the end. Then you define a query that you want to visualize. Here I am saying that I am interested in seeing the temperature variation. So that's the select query, and I want to group it by sensor ID. So instead of one sensor, if I had 10 of those, you would have seen 10 different lines on my graph. So that's the next thing, and this is how the graph looks like. So let me show you here. So you can see we have been collecting data for about last 1 hour. You remember we had a dip towards, when we did the demo of putting it in ice. Now the temperature came back up, or I think now the ice has started melting. So the temperature came up just little bit above 10 degrees centigrade. So it's about 13 now. So yeah, I think, yes. These are some of the, okay. Yeah, this is the last slide. One thing I would point out is if you are interested in learning about IoT, you might want to go to iot.eclipse.org. What that gives you is, it's a so basically what Eclipse has done is they have this IoT integration or IoT initiative that has about maybe more than 20 odd different open source projects. So they have open source pieces for Mosquito, Californium, which is for COAP. They have a software component that would let you update the code on your driver. So basically you would have different components for each of the requirement of IoT space. Same way, there are a couple of links about COAP or MQTT tutorial if you are interested in. And MapR has a quick start solution that you can use. So for example, if you are totally brand new to IoT environment and you just want to roll out your first application, we have a stream processing for real-time application which was built using, or this demo was built using that particular quick start. So it will get you started in 6 weeks. I think I ran out of time, so thanks. If anybody has any questions, if anybody has any questions, I'll be here to answer them. You can look at the demo in MapR booth. Yeah, and my email is there, so feel free to contact if you need more info.